So today we are going to talk about the homework of chapter 3. Okay, so for first question, we want to look at the problem 3.1. Here is to concentric sphere, okay, which have a radius A and B. And by azimuthal symmetry, we can know that the general potential field can be written as this form, which is okay, the same as what we used in lecture note. Okay, then by apply the boundary condition, we first to multiply the PL prime cosine theta on both terms, and then to eliminate the Legendre polynomial term to get AL and BL. Okay, so after integration, then we just use the boundary condition on R equals to A, and where the potential is equal to V as the cosine theta bigger than 0. Okay, and the same process, we apply the boundary condition on R equals to B, and then say the cosine theta below 0 is the potential is V. Okay, so by using these two boundary condition, then we can get these two formula. Okay, then we will find that in this formula there is a integration of the polynomial. Okay, PL of x dx, and in here we have the same term. Okay, so then we just to write down the integration general form, and we can look at it. For L equals to 0, this integration is equals to 1, and L is equals to odd L, then you will get this term. And when L is equal to even L, when L is even, then this integration will give us 0. Okay, so by this relation, then we can get our boundary condition. These two formula will become these two, and so by numerical calculation, then you can get the final phi of R and theta is equal to this term. Okay, very complex. So here we get our final result. Our potential phi is equal to this formula. Then we check the solution against the case. Okay, the first one is B will going to infinity. Now B going to infinity, you can easily check that your potential will become this term. And in another limit case, when A is going to 0, then you can easily check that the potential field will equal to this term. Okay. And then for the problem 2, here we have a spherical surface. Okay, spherical, and it's with a surface density Q over 4 pi r squared. So in here we just write down the potential field in general form with after matching the boundary condition. Okay, it will look like these two when r minus r less than big R and R bigger than big R. Okay, so we first want to calculate the charge density, surface charge density in the form of our general solution. So we just first calculate the electric potential and get our surface charge density as this term. Then we will get surface charge density as this. Then as we always do, then we just integrate the polynomial on both sides to eliminate this term to get our AL. Okay, so the integration, then we use the boundary condition on the charge density. As we know, when cos theta is less than cosine alpha, there is a charge density 2/4πr². And when cosine theta bigger than cosine alpha, there's no charge density on here, so this will equals to 0. So then we can know our AL will become this term. Okay, and then in here we use the polynomial. So okay, and then in this term we use the addition theory of polynomial. It will here of cosine theta is equal to 1/2L plus 1 times this P prime L plus 1 cosine theta minus P prime L minus 1 cosine theta. Okay, so we use this relation back into our integration, then we can easily get AL is equal to this term. Then after we get AL, we just substitute this term into we replace this term into our then we can get our potential will equals to these two formula as R less than big R and R bigger than R. Okay. Okay, and then we will want to find the direction of the electric field and the magnitude of the electric field, okay, at the origin. Okay, so we know that the electric field is equal to minus gradient phi as R equals to 0. Okay, so in this turn, we just need to calculate the partial derivative of phi with respect to the R and the theta. Okay, so we just do the numerical integration, numerical partial derivative. Okay, so we can get our electric field will equals to this term. And you will find that these two cosine theta in the R direction minus sin theta in the theta direction will equals to Z direction. Okay, so we can simplify our final result of electric field as this term. And for problem C, we want to check the limiting case. Okay, so first one, we will look at as the alpha very close to 0. Then you know that the cosine alpha as alpha very close to 0 will can be simplified as 1 minus 1/2 times alpha squared. Okay, as we use the Taylor's extension. Then our potential is equal to this term. So here we just need to calculate the PL plus 1 cos theta minus PL minus 1 cos alpha. Yeah, this term. So we just calculate these two. Then I some property of algebraic polynomial, then we can know that these two will become 2 times delta function with L0 minus 2 times L plus 1/2 times alpha squared. Okay, so we just replace these two. Replace the Legendre polynomial with this, and we can get our potential will equals to this formula. And you will find that in the this part, it's just the expansion of our green function, which is r minus big R in the z direction. Okay, so we can get our final potential as this, which is very similar to the result that you have a whole surface with the Q over with a charge density big Q. Okay, now it looks like the case you have a big Q on the surface and just missing one part, which is at z at r direction and with a point charge Q times alpha square over 4. Okay. Okay, and it makes sense in the physics meaning. And also we consider the second condition, which is alpha is very close to pi. Okay, so in here we just let our alpha is equals to pi minus beta, where beta is a very, very small angle. So by probably similar process, we substitute our these two polynomial. We replace this by this term and back into our potential field. Then we can get our final potential as this, and it will look like just a point charge with a charge Q times beta square over 4 in the minus R, position. Okay, so is fit the and this condition fit the physics meaning. Okay, so you can check. And for the problem 3.3, we have a same disk of a radius r in the xy plane. So we want to calculate the potential. Okay, so for first, we want to calculate the charge density. Okay, so as we derive in the chapter 1, maybe chapter 1, yeah, in the homework of chapter 1, then we can show that the charge potential is charge density. Sorry, charge density will equals to this term. Then we just use the boundary condition. R equals to 0, the potential will be V. Okay, so we just apply this boundary condition, then we calculate the integration to get the result. So by boundary condition, we can show that the lambda is equal to 4 times epsilon 0 times V over pi. Okay, so in here we can just finish our charge density. Okay, then we just put this charge density back into our potential equation, then expand it in the spherical coordinate. Okay, then okay, very complex, and then we solve the then we use the general form of R bigger than big R is equals to this term, and here is the integration of our work. Okay, so we just compare the 系数 coefficient. Yeah, we just compare the coefficient between these two. Then you will find that the AL big RL will equals to this integration form. And in this integration form, we only left this tricky integration. Then you can just apply this by computer. Then you can get this integration will become this compressed form. Then we just put this integration back into our coefficient. And after some numerical calculation, you will find that AL will equals to this when L is even, which means L is equals to 2 times n, the AL will become this term. And when L is odd, which means L is equals to 2 times n plus 1, and AL will become 0. So our potential will become this term. And when in this problem, we want to look at R bigger than big R will become this term. So in the problem B, we just use the result we derive in here. So we just substitute the R minus will when R less than big R, then the R minus R small. Okay, R small is the small r, and R big is big R. Okay, so yeah, we can check this. Then so the potential of R less than big R will become this term. Sorry, error type. Error type. Yeah. Oh, here is the error type. So the actual solution is here. Okay, sorry for that. And for the problem C, we want to capacitance of the disk. Okay, so we know that capacitor is equals to Q over V. So we just need to integration to get integration the charge density over whole volume. So we can get the total charge Q. Then after integration, we can easily calculate the capacity is equals to 8 times epsilon 0 times big R. Okay. And for final problem, we want to look at the 3.22. Okay. So here's the geometry of two-dimensional potential problem. Okay. So in here, first we want to know the very useful relation, that which is the delta psi minus psi prime will equals to 2 over beta times summation m from times psi of m pi phi over beta times phi prime over beta, where the prime means the point source. Okay, and the non-prime variable is the observer. Okay, it's the variation for observer. Okay, so first assume our green function as this general form, function times psi, and then we just use the Laplace equation, and we can know Laplace equation of green function will equals to the point source, the source, okay, our source. So to delta function. Then by the formula we have here, delta psi minus psi prime will equals to this term. So we can know that this term can be write as this term. We just replace the deltas minus prime. Okay, and by compare these two coefficients, then we can assume our AM is equals to minus 8 pi over beta times a small g function times psi, and this small g function is after we calculate this small g function, then we can get AM function and we can get our green function. Okay, so in here we just define a small g function to simplify our calculation. Okay, so as we define AM is equals to this, then this Laplace equation can be simplified as this formula. Okay, this relation. Okay, so here we just need to calculate this relation. Okay, with the boundary condition, our small g function when r equals 0 and r equals a will all become 0. Okay, that's our boundary condition. Then we can know that the general form of our small g function will become this two when r is smaller than r prime, rho is smaller than rho prime, and when rho is bigger than rho prime will become individually. Then we just use we just integrate this whole formula from rho prime minus epsilon to rho prime plus epsilon to eliminate the function. Okay, so we can get this form. And then we just calculate the partial derivative of r when r is r prime minus and r is r prime plus. Okay, so just do the very complex numerical calculation and you can get the coefficient here. A and B will become these two, and put A and B back into our general form of small g function, then we can get small g function will equals to these two. Then by simplify this, we can write the g function will equals to this with r big and r small. Okay, so in here we successfully get our small g function, and then we just put our small g function back into the AM function and put AM function back into our green function. Then we can get our final green function as this big term, okay, which is the same as the result we want in here. Okay, you can easy to check that these two is the same. Okay, so here is all our problem today. So if you have any question, you can ask me after the class.